Today I'd like to discuss the modes of a cosine slash parabola potential, one-dimensional. This potential consists of a cosine centered at 0 superimposed on a parabola. The cosine slash parabola potential has the advantage that all of its derivatives are continuous. The Schrodinger equation is the solution of the Schrodinger equation for a parabola is a simple product of exponential, Gaussian times a Hermite polynomial. In the case of we have potential wells on both sides of 0 here, two on each side. Now, any potential well, if you look at it close enough, if it's smooth, then it can be modeled as a parabola for a significant distance from its center. So here's a potential well on the left, and another one up here at a higher level on the left, as well as two on the right as well. Now, when you model the potential well as a parabola, you can calculate the modes directly for each of the potential wells. So in that case, I've done that here, and of course the lowest mode of a parabola is h bar times omega over 2. And that's what this is. So this is and also lambda, which is the energy for the lowest mode, is superimposed on that. So you can't see both curves 2 and 3 are overlapping. The next thing I'll show is the same potential, but for the first excited mode, really, of this particular parabola, and that it'll be 3 times as high. You notice that the omega over 2 is at 0.1, and and the green line is at 0.3. It's 3/2 omega. The next one I'll show is the case for 5/2 omega, where the energy is 5/2 omega. So that continues on up, but not much farther than this, because it starts running into the effects of the parabola and of the next cosine. So you don't expect it to continue. It's a little bit less than 5 times the omega over 2, which is what we expect to be if it were just a continuous parabola. So having said that, we'll start showing the modes. Now here's the lowest mode for that case. Now what it is simple Gaussian, because the first Hermite polynomial is just 1, and that's multiplied by a Gaussian, which is shown here. And there's 1 on each side. Now, if we go to the next one, we have one on the left, it's a -1, negative Gaussian. On the right, it's a positive Gaussian. Not much interest there. So now, on the next one, we have the first Hermite polynomial times a Gaussian, and it's odd with respect to the center of the first potential well, as expected. And of course we have 1 on each side, and here is the opposite scenario. Notice this swaps parity, we would call it. Okay, the next one is H2, which is 3 minus x squared times the Gaussian, and here we have a pair, one on each side, one centered on each of the two potential wells on the right side, on the left and right side. And here is another one, and this happens to be odd with respect to the center of the, I'm sorry, even with respect to the center. And while this one was also even, but it's just the this one here is just the negative of this one. So next we have the situation where the mode energy, which is green, it has exceeded the bottom of the next potential well, as you can see, and that allows the second potential well to be populated with another Gaussian, by the way, just very similar to the Gaussian we had in the first potential well. And this is the case for the next cited state. It happens to be what we call degenerate with respect to the other one. You notice there's a little bit of a blip there, small amount. Next we go back to the center, and we have a more complicated Hermite polynomial situation, but it's really not a Hermite polynomial anymore because the energy is significantly higher than the height of the Gaussian, and twice the height of the Gaussian, actually, twice the amplitude. So there's our next one. And here is an additional one. Notice that this one happens to be even with respect to the center of the Gaussian, and so does this one, center of the potential well, rather. So, and of course the energy is moving up on both of those. Here we have the second mode, the first excited mode really, centered on the second potential well. And that goes up, and you can see that it's going up higher. And this is the next one. In other words, it happens to be degenerate with the last one. Now we have a more complicated Gaussian, or sorry, more complicated mode in the center, more zero crossings. Zero crossings correspond to the number of nodes of the Schrodinger equation, wave function. This is the same thing. This is just the inverse of the last. These, by the way, are finite element solutions of the cosine / parabola potential. Another one going up higher. Here is the same thing, same energy. Yeah, a higher yet potential, and now we call the third excited mode centered on the higher potential well. Here we have the same thing, back to the center, and more nodes, as you can see. And here is a asymmetric mode in the center. Next one, it will be, all right, now we have the fourth excited mode centered on the two higher potential wells. Now we have that's just a repeat, and now we have the energy is sufficiently close to the top of the second harmonic of the second peak, that we can actually have some population of both the higher modes, higher potential energy as well as the lower too. Here we have that same thing. Okay, at this point we've just exceeded the peak here of the next to the higher potential wells, and now we've got a fairly even population in both of them. Here we are again, where we've actually gotten a slightly greater population in the higher potential wells than in the lower. And here we are fairly evenly distributed for the potential wells. By the way, the classical turnaround point is right here, where the green line intersects the potential, and you don't see an infinite the infinite value of the Schrodinger wave at that point. So that is a big difference from the classical case. Another thing you see is a big difference is that the wave function actually extends beyond the classical turnaround, and that is another difference. Now we have an even higher result for the energy, for the mode energy, as you can see it, the green line, and again pretty much fully populated in both the outer and the inner potential wells. More of the same. That was it for that.